So this question is a differential equation where we will first need to set up a differential equation. So we do this by taking information from the question. The first thing is we're told about a rate. So whenever we see a rate, we can replace it with the symbol dv over dt. So notice the t is for time, which is what indicated by the rate. And we can also see in the notation here, we're talking about centimetres cubed, hence a volume, and s to the minus 1 out of seconds, so therefore a time unit. So the first thing we know is we've got a constant rate, so we know that it's going at 40. However, if we read further, we find out we are leaking some container from the rate, and we're given a specific rate. So that's going down, and therefore we can now say we have got a differential equation of the form dv over dt is equal to 40, the positive rate, minus 1/4 v, which is the rate of decrease. So if we want to solve this, and we've been given some information that will allow us to get not just a general solution, but a particular solution, we can work through this. So the first thing we've got to realise is solving a differential equation requires the removal of these differentials. And the only way of moving differentials is through integration. So to integrate, we need to have things of the form of a product of some kind of function, either in terms of v or t, times by the relevant differential. So to get a product, we can only do this by multiplying and dividing. So we do not think about adding v over here and times in dt. We're going to have a whole lot of mess. We're not going to have a product. So we've got to think about how we could turn this into something that we could divide. And the simplest thing, if you've only got one variable, is to divide the whole thing by itself to get 1 on this side and the function of v on this side, and to multiply everything by dt, which is a bit questionable on some levels, but it will work out okay in the end. Before to make my life a bit easier, I might just tidy this up a little bit. So I'm going to suggest that if I times everything through by 4, I'll get rid of that fraction, because really, if we can get rid of fractions, we do make our lives a lot easier. Okay, so I've multiplied everything through by 4, and now I'm going to divide everything by 160 minus v. So on the left-hand side, I'll get 4 over 160 minus v dot dv. And I'm also going to multiply everything by dt. Well, all that's left on the side is 1, so in a sense, I'm going to get 1 dt. So what I've done is I've divided by 160 minus v, and I've also multiplied by dt. What I can see now is I've now got a function of v as a product of dv and a function of t, or in this case a constant, times dt. I now know that I can remove these dv's by integrating with respect to dv and v and dt and t. So on this side we're going to get, we've got to remind ourselves we've got a rational function here, so we're going to have to use the reverse chain rule. And using the reverse chain rule, and we're going to turn this into a log function. So we've got a 4 as a coefficient. The differential of 160 minus v will be minus 1 with respect to v, and therefore we're going to get minus 4 ln of 160 minus v. If you're struggling with the integration, well, that's a separate skill and not really what we're concerned with this topic of solving differential equations. On this side, we know it's got a 1. We're doing it with respect to dt this time, so we're going to get t, and here's the key thing. We need a constant. We don't need it on both sides, because in essence we can combine them to make kind of a super constant, but that's our plus c. Now, if we look at the question, it wants it in a particular form, and we haven't got that. Clearly, we need to make this v our subject. So we're just going to simply reverse this, and we'll notice an interesting result. So the first thing we're going to do is get rid of the minus 4, so that means we need to divide by minus 4, so we've got t plus c over 4, and this is where it gets a bit funny, because we can actually keep our c here, so we could actually replace that with t over minus 4, and we notice that's what we're looking for, and we can keep that as plus c at the moment, because again we haven't put any values in, so we can leave it as plus c. The next step now is to get rid of the log, so I'm going to have to go over here for my next step, and therefore 160 minus v must be equal to e to the t to the minus over minus 4 as per here, and we've got a plus c involved here. Now this is where a common point comes out, is we kind of know that this idea is quite common, isn't it? That we know that rule, our indice rule. So in this case, we can remove the c, and you'll quite often see the constant being replaced. I'm now changing it to minus quarter t, so it's the same as here. We quite often represent the constant, and really this a is representing e to the c in this case. Okay, and we've still got our 160 minus v, and so our final bit is we can see where we got our a come from, and we got a times minus 1. So the final thing will be to do those two steps. So if we do that, we get 160 minus a e to the minus quarter t. Okay. However, we did want to find out what a is, so to do that, we're going to turn it in from a general solution, which is what we have here, into a particular solution by finding the value of a. And we do that by going back to this information here, where v is 5,000 and t is equal to 0, which means that when t is 0, e to the 0 will be 1, 160 minus v will be equal to a, and we can replace v with 5,000. So what we'll discover if we do this correctly is that minus 4,840 will be equal to a. And that's because v is equal to 5,000 when t is equal to 0. So now we can complete our equation for a particular solution. And if we wanted to, we could check it by putting 0 in and checking that this did indeed equal 5,000, which it does, of course. Now, to complete the question, well, we have completed the question, but we might want to make clear that a is therefore equal to 160 and b is equal to 4840. And that's how we solve a differential equation.